The holidays start here at Baker's with a variety of options to celebrate traditions old and new. You could do a classic herb-roasted turkey or spice it up and make turkey tacos. Serve up a go-to shrimp cocktail or use Simple Truth wild-caught shrimp for your first Cajun risotto. Make creamy mac and cheese or a spinach artichoke fondue from our selection of Murray's cheese. No matter how you shop, Baker's has all the freshest ingredients to embrace all your holiday traditions. Baker's, fresh for everyone.
This is SpaceTime, Series 19, Episode 76, for broadcast on the 28th of October, 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, solving the mystery of the millions of missing stars, evidence that Uranus may have additional unseen moons, and new images show that meteoroids are hitting our moon at least 100 times more frequently than previously thought. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Galactic cannibalism may finally be the clue to solving the mystery of the millions of missing stars at the centres of some of the biggest galaxies. A new study reported in the Astrophysical Journal, which examined the galactic cores of two of the largest known galaxies, has opened a new window into the processes that shape the evolution of massive galaxies. One of the study's authors, Professor Alistair Graham from the Swinburne University of Technology in Melbourne, says for the last few decades astronomers have noticed a star shortage in the centres of some of the biggest galaxies. Now, while investigating two large galaxies, each roughly 4 billion light-years away, almost a third of the way across the universe, Graham and colleagues may have finally solved the cosmic whodunit. And believe it or not, the main culprits aren't the usual suspects. The larger of the two galaxies, known as 2 Mass X J17222717 plus 3207571, is some 75 times more massive than our own galaxy, the Milky Way, and is the brightest galaxy in a huge galaxy cluster located in the direction of the constellation Hercules. The other smaller galaxy, known as 2 Mass X J09194427 plus 5622012, is near the constellation Ursa Major. It contains a slightly smaller galactic core, but overall it's still some 30 times more massive than the Milky Way. The authors have confirmed that one of the depleted cores in these two galaxies is the largest ever detected, and they believe it may not have formed in the manner previously thought. In normal-sized galaxies, such as the Milky Way, the density of stars tends to increase smoothly as you move towards the galactic centre. However, the less massive of the two galaxies being observed by Graham and colleagues appears to contain a smaller depleted core, likely formed by the collision of two similar-sized galaxies, each seeded with a central supermassive black hole several billions of times the mass of our Sun. In these galactic collisions, the supermassive black holes from each of the two colliding galaxies tend to migrate towards the centre of the newly created merged galaxy by flinging out the stars already there, literally hurling them outwards in a gravitational tidal slingshot. Meanwhile, those stars less fortunate, which venture too close to the black holes, are likely to be ripped apart and swallowed, disappearing forever beyond the black hole's event horizon. These cataclysmic events produce high-energy ultraviolet and X-ray flares, as each star's multi-million-degree core is exposed as it's shredded by the immense gravitational field surrounding each of the black holes. Graham says when the black holes themselves finally merge, a series of gravitational waves are also emitted. However, simulations have shown that if a galaxy collision involves a larger galaxy consuming a smaller satellite galaxy, a process called galactic cannibalism, things can be somewhat different. If the captured smaller galaxy has a densely crowded centre of its own, then this tightly bound central region can survive largely intact during the cannibalistic affair, with only the outer stars being stripped off. During this process, the captured galaxy migrates towards the centre of the larger galaxy in a braking process that literally pumps stars out of the core of the larger galaxy. Computer simulations have shown that they do this in such a way that a core of constant stellar density is created, around which the semi-digested stars then hover. Unlike the smaller of the two galaxies studied by the team, the stars in the core of the bigger galaxy are uniform in their distribution, and this galaxy also contains several dense knots of stars near the edge of its core. One of these knots measured a massive 45 billion times the mass of our Sun. Now, when you think about it, that's almost equivalent to the entire stellar mass of the Milky Way. Furthermore, the larger galaxy's giant core, discovered in 2012 by Mark Postman from the Space Telescope Science Institute in Baltimore, Maryland, is unusual in that it's some 10 times larger than those typically observed in other galaxies. Graham suspects this giant core was primarily formed from captured satellite galaxies, rather than massive black holes. Indeed, the culprits appear to have quite literally been caught in the act.
We've been studying two galaxies, and we thought from the beginning that the missing stars had probably been either eaten, swallowed whole, or gravitationally slingshot out of the centres of these two large galaxies. But one of the galaxies has such a massive depleted core, it's missing 100 billion stars, that black holes they weren't actually big enough to do so much damage. So we think a different scenario may have unfolded. We think the large galaxy has captured some of its nearby satellite galaxies. Now, in so doing, the galaxies themselves, they fall towards the centre, but they do so in a process which ejects stars out of the centre of the large galaxy. And we can see in the Hubble Space Telescope image remnants of 5 galaxies which have been partially digested by this large galaxy hovering around the core of this big galaxy. So that is, we think that we've observed the culprit for depleting the massive core.
You were seeing this using the Hubble Space Telescope, and to me this is the mind-blowing thing about it. This thing is a third of the way across the universe. It's 4 billion light years away. That's amazing.
Indeed it is. It's very far away. So what we observe today actually happened 4 billion years ago, but it's taken light that much time to travel across the universe to reach our telescopes. It also means that if we were to transport ourselves to the galaxy we are observing, that is, if we were right on its doorstep today, it's had 4 billion years to evolve, and the core could be much greater than what we observe.
Because that's almost the age of the solar system when you think about it, 4 billion years.
It is. A lot can happen in that time.
That big galaxy wasn't the only one you looked at. There was another one about the same distance away towards the constellation Ursa Major too.
That's right, yes, the Big Dipper. A little hard to see from Melbourne, but if you're in the north of Australia during the summer months, you can actually get a glimpse of that. Although the targets that we're looking at, they are very faint. So you can see the constellation, you can look in the direction of the galaxies we've been observing, but you won't actually see them with your naked eye. I will add, the smaller galaxy that we observed, it also is missing a lot of stars from its core, but the amount of stars which are missing, we think that massive black holes, that is, black holes with 1 billion times the mass of our Sun, we think they could have caused the damage in that galaxy. But in the larger galaxy, with the very large depleted core, and when I say very large, it's about over 20,000 light years across, 100 billion stars missing, we think that the infalling satellite galaxies, which are bigger than massive black holes, they can be 10 or 100 billion solar masses, the galaxies, and therefore being more massive, they can cause more damage. We think that these infalling satellite galaxies have removed the stars from the centre of this giant galaxy with the giant partially depleted core.
Is this really another form of environmental quenching?
It is in a way. If you are a galaxy that is forming stars, if it has gas which can condense and form new stars, if that galaxy was to fall into a big galaxy, it's going to lose the ability to hang on to its gas, and so it loses the ability to form new stars.
So it's the same sort of gravitational process at work here.
It is. We call it a range of things, stripping of the gas. Sometimes astronomers use the term strangulation.
Well, that's a good one. I like that one.
That's a choking off of the gas supply in the halo of a galaxy. There are others.
Were you guys suspecting there must be another possible cause for this dearth of stars in the galactic centres of some of the biggest galaxies, simply because black holes couldn't explain it, so there had to be something else doing it?
Yes. The biggest thing which tipped us off and made us look into this system was the extent of the partially depleted core. Being over 20,000 light years across, it's roughly 10 times larger than the sizes of partially depleted cores in other big galaxies. So the first thing we wanted to do was to check, is there really such a large depleted core in in this galaxy, modelled the galaxy, subtracted off all of the foreground and background contaminant stars that one sees in these images, and measured the distribution of light in the star, convinced ourselves that indeed there is a very large deficit of stars in the galaxy, and then we thought, this is so big, black holes are probably not the culprits responsible for causing the damage to the heart of this galaxy.
And as you were looking at these stars in the larger galaxy, or the lack thereof, you saw these massive, you've described them as dense stellar knots. And some of them, I mean, these figures are amazing. 45 billion times the mass of our sun. That's like the stellar mass of our entire galaxy, isn't it?
You're right, that is. And those galaxies were probably bigger. What we believe we're seeing, these knots of star clusters, they are the semi-digested galaxies which the larger galaxies captured. So they could have been twice as big. What's happened is the stars in the outer part of these captured galaxies have been stripped off as they've fallen into the large galaxy, a bit like evaporation, if you like. And what's left behind is the tightly bound nucleus or core of the captured galaxies. We've seen 5 of them, which means there are 5 galaxies that have fallen in and can act on depleting the stars from the centre of the large galaxy.
And of course, these events, these galactic collisions, they're not just something that happens in the distant universe. All galaxies seem to grow through merging or cannibalism, and that includes our own Milky Way, both in the past and in about 3.8 billion years from now, with Andromeda in the future as well.
Yes, that's right. The universe is a violent place. It was and it still is. Nature doesn't seem to have any morals. The big prey on the small.
As we look around, we're seeing lots of these tidal streams of stars, which is clear evidence of mergers.
It is indeed true. Mergers, we've always known they occur, but we're now starting to, I think, more fully appreciate just how important they are in building up galaxies over time. And one thing which wasn't fully appreciated was that mergers, if you have 2 galaxies of a comparable mass collide, we used to think, you're going to end up with a big mess. You'll end up with an elliptical-shaped galaxy. But it's not always the case. Sometimes you can form a disk. So you have a central bulge of stars surrounded by a disk of rotating material. And so the mergers can actually give rise to ordered motion in galaxies, which wasn't always appreciated before.
We're finding out a lot about galactic evolution through these sort of studies, aren't we?
Oh, yes. We haven't got all the answers yet, but some things are coming into focus. One thing which I think hasn't been fully appreciated in the past is the formation of disks in galaxies. We used to think if mergers occur with infalling systems at random orientations, you'll just end up with a big mess, a big elliptical galaxy. But the way the universe seems to work is that the infalling captured galaxies, they tend to line up in a plane and contribute to the growth of disks in galaxies. So we have this structured, ordered rotation rather than simply a big mess.
That's Professor Alistair Graham from the Swinburne University of Technology in Melbourne. And it's worth pointing out that the future James Webb Space Telescope, expected to be launched aboard an Ariane 5 from the European Space Agency's Kourou spaceport in French Guiana in 2018, will enable astronomers to better image more galaxy cores and hopefully reveal just how often hapless satellite galaxies are consumed. There's growing evidence that the planet Uranus may have another 2 as yet undiscovered moons. A report on the pre-press physics website archive.org claims unusual patterns just detected in 2 of Uranus's dark rings could indicate the presence of 2 small moonlets, each between around 4 and 14 kilometres in diameter. Astronomers Rob Chancellor and Matthew Hedman from the University of Idaho noticed the ring patterns when they were re-examining old images taken 30 years ago by NASA's Voyager 2 spacecraft as it flew by the 7th planet from the Sun back in 1986. They detected periodic variations in the amount of material on the edge of the Alpha Ring, one of the brightest of Uranus's multiple rings. And a similar, even more promising pattern was seen in the same part of the neighbouring Beta Ring. As they examined the pattern in different places around the rings, they noticed changes in the wavelength, which indicate something was breaking the symmetry as one goes around the ring. Chancellor and Hedman are both well versed in the physics of planetary rings. Both have studied Saturn's rings using data from NASA's Cassini spacecraft, which is orbiting the Saturnian system. Data from Cassini has yielded new ideas about how rings behave, and a grant from NASA allowed the authors to use those new ideas to examine Uranus's data gathered by Voyager 2 in a new light. They analysed radio occultations, made when Voyager 2 sent radio waves through the rings to be detected back on Earth. And the team also analysed stellar occultations, made when the spacecraft measured light from background stars shining through the rings, which helps reveal how much material each ring contains. They found the patterns in Uranus's rings were similar to moon-related structures in Saturn's rings known as moonlet wakes. The authors estimate these hypothesised moonlets would have to be much smaller than any of Uranus's 27 known moons. Uranus's moons are especially hard to spot because they're made of a mix of frozen water ice and unknown other materials which give them an extremely low albedo. Albedo is a measure of light reflectivity or brightness. The new findings could help explain some characteristics of Uranus's rings, which are strangely narrow compared to most of Saturn's rings. It's thought the moonlets, if they exist, may be acting as shepherd moons, helping to keep the rings from spreading out. Two other Uranus moons, Ophelia and Cordelia, also act as shepherds, keeping the planet's epsilon ring confined. The problem of keeping rings narrow has been around since the discovery of the Uranian ring system back in 1977, and it's been worked on by many different dynamicists over the years. Astronomers will now begin poring over spacecraft and telescope images to try and confirm the existence of these two potential new moons. And if these proposed moonlets do turn out to be real, astronomers will be able to use that data for future studies. A new study has found that small meteoroids are hitting the Earth's moon at least 100 times more frequently than previously thought. The findings, reported in the journal Nature, are based on high-resolution lunar images and raise fresh concerns about future long-term human exploration of the lunar surface. The study's lead author Emerson Speirer from Arizona State University says scientists thought it took hundreds of thousands to maybe millions of years to change the lunar surface layer significantly. But they now know the moon's surface is being completely churned over by small meteoroid impacts in something like 80,000 years. The new results are based on images taken by NASA's Lunar Reconnaissance Orbiter, which was launched back in 2009. The images indicate that lunar surface features already believed to be young are perhaps even younger than assumed. It also means any structures placed on the moon as part of future human expeditions will need to be better protected. Scientists reached their conclusions after comparing before and after images taken by the Lunar Reconnaissance Orbiter's narrow-angle camera over the 7 years that the mission has run so far. The team identified 222 new impact craters that formed during the mission, ranging in size from just a few metres wide up to 43 metres across. The number of new craters found is far greater than that anticipated by standard impact modelling rates currently being used by lunar scientists. The discovery has the effect of giving lunar surface features younger ages. Measuring the current rate of meteoroid impact on the moon was one of the primary missions of the Lunar Reconnaissance Orbiter. Besides the value to scientists in pinning down surface ages, there are also practical aspects. That's because any future human exploration of the moon will involve supply structures, rockets and other equipment being parked on the lunar surface for long periods of time, even if living quarters are built underground. Knowing the present-day rate of impact will be important in planning to protect equipment left on the surface. When the team examined the new craters found by the Lunar Reconnaissance Orbiter survey, they noticed that the craters were surrounded by starburst patterns that were obviously formed during the impact. While the pattern details are complex, the authors found that an impact throws out several different kinds of debris. Some of it lands nearby, but these impacts also throw out small amounts of debris in hypervelocity jets at speeds of up to 16 kilometres per second. This material, in the form of vaporized and molten rock, shoots over the surface, disturbing the upper layer of lunar soil and changing its brightness. In addition to the new impact craters and starburst debris patterns, the research team also observed a surprising number of small surface changes, which they've nicknamed splotches. Splotches lack the detectable rims of craters. They're thought to be more likely caused by ejected debris material thrown out of the larger impact craters. The authors found dense clusters of splotches around new impact sites. That suggests that many splotches may be secondary effects caused by material thrown out of the primary impact event. From some 14,000 pairs of before and after images, scientists identified more than 47,000 splotches. By estimating their accumulation over time and measuring their sizes, the authors were able to infer just how deeply each splotch dug up the surface. That gave them an estimate of just how long it takes to effectively churn or garden, for want of a better term, the upper few centimetres of lunar dirt. The gardening time is amounted to a geological blink of an eye, not millions of years, not even hundreds of thousands of years. In fact, they've calculated that 99% of the surface of the moon was being overturned by forming splotches about every 81,000 years. Earlier estimates had considered only direct hits from micrometeorites and ignored entirely the role of small secondary impacts. This means that future remote sensing observations of the lunar surface will now need to factor in a much higher turnover rate, especially when looking at data from mineral-detecting X-ray and gamma-ray spectrometers which probe the upper surface layers. It also means this churning rate will be important new information for future planners of moon bases. Surface assets will need to be designed to withstand the impacts of small particles travelling up to 500 metres per second. And as the Lunar Reconnaissance Orbiter's mission continues, the odds are increasing for scientists' chances of finding larger impacts that occur less frequently on the moon. Such discoveries will let astronomers better pin down lunar impact rates and also better characterise these most common processes that shape planetary bodies across our solar system. As Titan approaches its northern summer solstice, NASA's Cassini spacecraft has revealed dramatic seasonal changes in the atmospheric temperature and composition of Saturn's largest moon. Winter is taking a strong grip on Titan's southern hemisphere, and a strong vortex enriched in trace gases has developed in the upper atmosphere over the South Pole. These observations show a polar reversal in Titan's atmosphere since Cassini arrived at Saturn in 2004, when similar features were seen in the moon's northern hemisphere. Cassini's long mission and frequent visits to Titan have allowed astronomers to observe the pattern of seasonal changes on Titan in exquisite detail for the first time. Cassini arrived during the northern hemisphere midwinter, and astronomers have now had the opportunity to monitor Titan's atmospheric response through 2 full seasons. Since the equinox, both hemispheres received equal heating from the sun, and they've seen rapid changes. They've discovered that heat is circulated through Titan's atmosphere by way of a pole-to-pole cycle of warm gases upwelling at the summer poles and cold gases subsiding at the winter pole. Cassini's observations showed a large-scale reversal of this system immediately after the equinox in 2009. Amazingly, it seems Titan's hemispheres have responded in different ways to these seasonal changes. The wintry effects have led to a temperature drop of over 40 degrees Celsius at Titan's southern polar stratosphere over the last 4 years. This contrasts strongly with a much more gradual warming in the northern hemisphere, where temperatures have remained stable during the early spring and have shown just a 6-degree increase since 2014. Within months following the equinox, the vortex in the stratosphere over the South Pole has become prominent, as has an atmospheric hotspot at high altitudes. The corresponding features in the northern hemisphere had almost disappeared by 2011. Inside the polar vortex over the now increasingly shadowed South Pole, there's been a rapid build-up of trace gases that accumulate in the absence of ultraviolet sunlight. These include complex hydrocarbons and nitriles such as methylacetylene and benzene, previously seen only at high northern latitudes. Scientists say it's given them the chance to witness the onset of winter from the beginning, and they're now approaching peak time for these gas production processes in the southern hemisphere. Making these detections will help scientists better understand the photochemistry going on. In the northern hemisphere, the trace gases have persisted well into summer. These are now expected to undergo a slow photochemical destruction, with species disappearing at different rates depending on their chemical lifetimes. However, since early 2016, a zone of depleted molecular gas and aerosols have developed across the entire northern hemisphere, between an altitude of 400 and 500 kilometres, suggesting a complex dynamical effect starting at high altitudes in the atmosphere. As astronomers count down to the end of Cassini's mission in September next year, a consistent picture of Titan's middle and upper atmosphere is starting to emerge. The 13-year total mission duration will in the end provide scientists with coverage of almost a full half of Titan's year, in the process providing a deeper understanding of Titan's seasonal variability. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGarry.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.